Then we'll start. Yeah, so meanwhile, I think Monday onwards, the second entrance starts, right? Anyone can respond.
Yes, sir.
Yeah, so people know the information, right?
Yes, sir.
Yeah. Okay, so since other section, I don't know whether what they are, how much they have covered in terms of the syllabus. Okay, but for the second entrance, the third unit complete. Okay, and from the second unit, you will start from the RC delay models. Okay, so you'll have one topic in second unit, RC delay models, and the third unit will be complete. Okay, is that clear, all of you? Anubhav?
Yes, sir.
Yeah, so that will be the syllabus for your second entrance. RC delay, starting from RC delay, complete third unit. Okay, so I thought of introducing, today onwards we start the fourth unit with respect to sequential MOS logic circuits. But the other section they are lagging behind, so that's why we are not including the fourth unit contents. Okay, so we will have this fourth unit for the third entrance. Okay, so with this information, we'll start actually yesterday's class, not the today's class. Okay, so because of the network issue, I couldn't continue there. Okay, so sequential MOS logic circuits. Okay, so till now you have been doing all your combinational logic using your CMOS. Okay, so maybe schematic or the layout. So this particular unit, okay, comprises of uh, sequential MOS logic circuits. Okay, and most of the sequential MOS logic circuit uh, from your third semester. Okay, so what is a sequential logic? Anyone can define what is sequential logic? Can anyone define what is a sequential logic now? Yeah, doesn't depend or depend? Okay, okay. So circuits whose output, okay, depends both on present input and plus or and the previous output. Okay, so this is what the definition of sequential. Any other definition anyone can give? Any other definition? Yeah. Any other definition of sequential logic in terms of combinational?
Combinational with memory element.
Excellent. So combinational logic, okay, plus the memory. Okay, so this is what your sequential logic is all about. Yeah, that's what we mean by basic example of sequential logic. Yeah.
Flip-flop.
Yeah, I mean the best example or the basic example becomes the flip-flop. Okay, and if you want to define something in terms of your combination plus the memory, okay, I have this as my combinational logic. Combinational logic or the circuit, whatever it may be. Okay, it has inputs. Yeah, call it as something like A, B, C. Yeah, it will produce output. Output 1, output 2. Okay, so you can see that there are more than one outputs, and you can have a kind of feedback, and that's what we mean by the memory. Okay, and this is how exactly it will go. Yes. Okay, so this is all about your sequential logic. Yeah, and the best example of starting or basic example of sequential logic is your flip-flop that's where mentioned there. Okay, and in that, when I say a flip-flop, there are 3 versions of flip-flops, right? Which are those? Yeah, first comes the latch, then comes the master slave flip-flops, and the third one comes the edge triggered flip-flops. Okay, so these were the 3 category of flip-flops we have. The latch. Okay, a latch may be a simple latch or it may be clock enabled, we call clock enabled. Okay, latch. Okay, something like this. Okay, so we'll try to see what all these things are all about. Okay, so this is all about your sequential logic, the definition, the example, the circuit, the way in which you can define, and then the 3 types of flip-flops here. And now then, when I say a latch, okay, one can be without any clock enabled. Okay, and one thing may be enabled. Okay, clock enabled or without any enabling way. Okay, so first we'll see an example of latch and how to implement these latches. Okay, using your CMOS. Okay, so that's what it's all about. Okay? So latch, again, when I say latch, there is NOR based latch. And basically, we mean by SR latch. Okay, one is NOR based SR latch. Second one we have NAND based SR latch. Okay, these are the 2 latches we have. Okay, and the corresponding circuit. Okay, how this latches goes ahead. Okay, so first one, the NOR based SR latch, and make sure that all your different types of flip-flops, okay, is based on your SR latch. Okay, so that is the SR latch forms the basis for constructing any of the other flip-flops like D flip-flop, the T flip-flop, the JK flip-flop and all. Okay, and the NOR based, why we say NOR based is typically with respect to we use the NOR gates. Okay, this is NOR gate 1, and we have the second NOR gate. Okay, this is a kind of recap for you people. Okay, but it makes sense for me to deal all these things because we have to deal with all the CMOS logic of this sequential logic. Okay, This one. So this is my S, this is my R, this is the feedback that I'm getting from here. This is the feedback that I'm getting from here. Okay. This is Q bar and this is my Q. This is what we, and then corresponding, since we have two inputs S and R, we have two outputs Q and Q bar. So basically Q and Q bar, they are complement to each other. Okay, so this device not only provides me the uncomplement value, but also it provides me the complement value. That is the meaning of that. Okay, so then we have four combination of input 0, 0, 0, 1, 1, 0 and 1, 1. Okay, so this is what the truth table goes like. Okay, this is how it goes. Now, as we know, we directly doesn't go with the analysis of this SR latch with a NOR or NAND, either for 0, 0 or 1, 1 combination. First, we'll go with the complement value of S and R. Okay, so S0 R1. Okay, for S0 and R1. And how we can define the NOR logic? Anyone can define the NOR logic now? In order to understand the operation of this NOR based SR latch, how to define this NOR? Okay, that's good. So NOR logic, if one input is 1 means output will be definitely 0. This is what we have. Okay, so in these two, for these two NOR gates that we have, NOR gate 1 and 2. Okay, one of the input of NOR gate 2 is 1, so simply I can say that its output is 0. That is, the NOR gate 2 output is 0, and this 0 is now fed back as an input to this now. Okay, and now with one input as 0 for the NOR gate 1, I can't define my output. The moment I have the other input also, now I can define 0, 0 means it is becoming 1. Again, if I just want to cross check whether the output of NOR gate 2 is 0 or 1 not, I can do this. Okay, get the feedback 1 or 1 is 1, its complement is 0. So that's what. So when it is 0, 1, Q is 0, Q bar is 1. Okay, that's what. And what we call this condition as? And what we call this condition as? When S0 R1,
Reset.
it is a reset. Okay, or clear. Okay. And now when I go for 1, 1, okay, I'll just use this. Okay, I'll just change these things now. Okay, so ensure that now S is 1. Just change this. Now S is 1, R is 0 for me. Okay, so the moment I have these, okay, assuming I don't know what is my previous. Okay, so now I can define the output of the first NOR gate, because one of the input is 1. I least worry about the other, so output becomes 0 here. And this goes as an feedback input for the second. And now this becomes now 1. Okay, and this goes as input for this. Again, I can cross check 1 and 1. 1 or 1 is 1, its complement is 0. So when S is 1, R is 0, I have 1 and 0, and this is what we mean by set. Okay, and this is what we have. Now, both the inputs for S and R is 0, 0. Okay, I have to just change this. S 0, R 0. So now I can't define the output of either the NOR gate 1 output or the NOR gate 2 output. Okay, that's why the previous output comes into picture now. So previous to this input S0 R0, I had previous input as S1 and R0. This is my previous input, and whatever the 0, 1 I am having here, this is my previous output. This is previous output, and this is my previous output. Okay, now this previous out act as an input, as we have already mentioned here. One is having over here. Okay, now we can see that S0, the other input for the NOR gate 1 is 1. So one of the input is 1, output is 0. That means there is no change in Q bar. And this 0 is again going here, and there is no change in the previous also. 0, 0 means it is 1 now. So you can see that when S is 0 and R is 0, there is no change in the output, and the same thing happens when Q bar is 1 and Q is 0 also. So that's why this I call it as n plus 1, Qn plus 1 bar, just to ensure that when both S and R are 0, 0, it is Qn and this is Qn bar. Okay. This is the third input combination that we have. So that means there is a no change. This is the no change condition. And finally, when we have the S and the R input, okay, when we have finally the S and the R input as 1 and 1, okay, and we have already defined NOR logic. One of the input is 1, output is 0. Both Q bar tends to become 0 as well as Q, and it is not the desired one, right? So when Q is 0, Q bar also 0 means it is undefined. So that's why we call this as something like undefined. This is what the logic is all about, right? So this is the NOR based SR latch. Similarly, now we can construct the CMOS logic, okay, SR latch. Okay, this is what we'll try to do now. So what all we want in order to construct, we want two NOR gate, okay, and we know that how to construct a NOR gate using CMOS, right? So NOR logic, it is basically a single stage NOR, each gate, okay. So this I call it as 1 and 2. Similarly, so when I'm defining my NMOS, this is what I have. My NMOS should be in parallel because it is a NOR, okay. That is the complement of OR. OR defining is in terms of this. So this is, I call it as M1, this is M2. So M1, M2 are NMOS 1 and NMOS 2, and the source of which are grounded, and the drains of which are shorted. Okay, so this is M1, M2. Now I have the PMOS logic. Just a minute. I have a PMOS logic on the top. Okay, so which has NMOS in parallel. So my PMOS in series I should have. Okay, this is my VDD, and this is with respect to NOR gate 1 that we have in the circuit. Okay, so the schematic, whatever we have, okay, so we are doing, okay, this is my NOR gate 1 where one of the input is yes, okay, and this is basically my Q bar. Okay, so NOR gate 1 output is Q bar, one of the input is S, this is what we are defining, and other input is actually the output of the second, and that's what we are going to construct towards the right of that. Once again, we have second NOR gate with M3 and M4. Okay, so and these two sources are common and they are grounded, and this is typically for my NOR2. Okay. And gates are shorted. These are the drain. One of the input is R for this, and the right side I'm writing the R. And similarly, I have the PMOS connected in series. Okay. This is what I'm having, and this is basically my Q. Okay, and as we know, So this and this becomes common. Okay. So one of the input for M, this is common now. And now the other input is common. And what should be connected to this point now? What should be the gate of M2? Yes? What should be the gate of M2? Similarly, what should be the gate of M3 now? Fast? Hello? What output?
Q1, Q1.
What should be the gate input for M2? Okay, and also for this BMOS transistor. Yeah, so make sure that from where exactly you will be connecting. Okay, this is what your Q. That means this is getting Q. This is S. This is Q. Okay, and similarly for this M3, I have the Q bar. This is Q bar, and this is my Q bar. So this is your CMOS logic for SR latch. Okay, it is a kind of output of one NOR gate acting as one of the input of the other NOR gate. Similarly, output of NOR gate 2 is acting as one of the input for the NOR gate 1. Hope this is fine now. Okay, so this is your CMOS logic for SR latch. Any clarification doubts? Only thing, make sure that you are not using your SR inputs as 1, 1. Okay, so you won't be providing S and R value 1, 1. Okay, apart from that, you can just do this. Is this clear now? Fast. Shall we proceed or not? What exactly? Yes. Yeah. Okay. Then there is something called again. So, for example, when I have S is equal to 1 and R is equal to 0, okay, this is what the condition is all about. What I want Q to be when S is 1 and R is 0?
1.
Q to be 1 and its complement Q bar should be 0. Is that okay? So that's what we want. Now, this entire two NOR gates, okay, these two I'm speaking about, okay, this is what, okay, this is what SR latch, okay. Now I have to ensure, okay, now I have to ensure that when S is equal to 1, R is equal to 0, okay, so the delay aspect, the worst case delay, okay, that is the tau of SR latch. Can anyone tell me what will be the delay of this SR latch, the CMOS SR latch? And for that, I'm just ensuring that this is the capacitance with respect to my CQ output, and this is the output capacitance with respect to Q bar. Yeah, because see, basically your any logic is with respect to the charging and discharging, right? Okay, it's basically charging and discharging. Yeah, basically charging and discharging, and that's what I'm doing here, right? So your wherever the Q is there, I'm connecting it to one capacitor, and Q bar is another capacitor. So CQ is basically the capacitor with respect to Q, and CQ bar is capacitor, output capacitance of the NOR gate. Okay. So when I want to calculate the worst case delay, okay, of this SR latch when S is 1, R is 0 is, that is two things. One is there is a rise time happening with respect to my NOR 1, okay, NOR 2 basically, okay, Q is with respect to NOR 2, okay, and there is a fall happening with respect to the NOR one. So the total delay, that is the tau of this SR latch, is given by now tau of, that is the rise of NOR 2. Okay, it is the time taken or the RC delay with respect to rising of NOR 2 from 0 to 1 plus the fall time, that is the tau of fall with respect to NOR 1. Okay, so this is what the combination of rise time of NOR 2 plus the rise fall time of NOR 1 is equal to the total delay with respect to SR latch. Hope this is fine. This is one. So what if S is equal to 0 and R is equal to 0 now? Yes. I just go to the next slide. Okay. My question is simple. When S is equal to 1, R is equal to 0. Okay. I add Q to be 1, Q bar to be 0, and Q is basically the output of NOR 2, and Q bar is the output of NOR 1, right? So for this combination, the total delay of SR latch was equal to the rise time of NOR 2 plus the fall time of NOR 1. Okay. The RC delay of NOR 2 and the RC delay of NOR combination gives you this. Now my question was, what will be, and Q is no change, that is the previous, this is N plus 1, I take N plus 1, and Qn plus 1 bar, that is the next step will be its previous, right? Qn bar. So now tell me, what is the time delay of the SR latch now? Anyone? Yes? Yes?
0.
It is minimum, that is 0. That's what I'm saying. Okay, now when S is equal to 0 and R is equal to 1, we have Qn plus 1 is equal to 0 and Qn plus 1 bar, that is the complement output, is 1. So now what is the time delay or the delay of the SR latch now? Yes? Fast.
Tau fall of NOR 1 and tau rise of NOR 2.
Tau fall of NOR 2 plus tau rise of NOR 1. Okay, so this is, and the worst case, if you see, this is not the worst case. The worst case delay means the maximum delay. So this is the minimum delay I'm having in the SR latch. And what is the maximum delay or the worst case delay I'm having? For which conditions I'm having the worst case delay?
Sir, both 1-1, sir.
Yeah, both 1-1 now. So 1-1 is an invalid for me, boss.
0-1 and 1-0, both.
S is equal to 1 and R is equal to 1 is an invalid condition. I need not apply any input for that. This is the important one. Yes. So when S is 1, R is 0, or when S is 0, R is 1, I am getting the worst case SR latch delay. Hope this is fine. Yes. Is that okay? How to calculate the delay in terms of the SR latch? Yeah. And for what conditions of S and R, what is the RC delay I'm getting with respect to the SR latch? And what is its worst case delay and what is its minimum delay? Minimum delay when both S and R are 0, 0. That means output there won't be any change. When there is no change, I mean my R and C will be remaining 0 itself. Okay. And this is all about your construction of the CMOS logic SR latch. Okay. And this is basically a NOR based, right? So this is basically a NOR based. This is NOR logic based CMOS logic that ensures about SR latch. Is that okay? Yeah, any clarification doubts till this point so that we can move ahead now? Yes, no. Fast. Shall we, yeah, so we'll move ahead. Okay. So now we'll go with the NAND based. Okay. We'll go with the NAND based SR latch. The NAND based SR latch. Okay. So now we'll be using NAND gates instead of the NOR. This is NAND gate 1 and this is my NAND gate. Again, we have a feedback mechanism. This is S bar, this is R bar, this is my Q, this is my Q bar. Okay. So why we are providing S, why this S bar R bar, you'll understand now. Okay. So I'll just go with SR. Correspondingly, I will have S bar R bar. Then it is Q. I call this as something like Qn plus 1, Qn plus 1 bar, Qn plus 1, Qn plus 1 bar. Okay. This is what I have. Okay, so again, yeah. So when S is 0, R is 0, what will be my S bar, R bar? They are 1 and 1. Okay, so this is important for us. Already been taught, but still a recap of this. And how we can define a NAND logic? How we can define a NAND logic?
If a one input is 0, output is 1.
Yes. If any one input is 0, okay, of NAND logic, output will be simply 1. That is what we have. Okay, that is what. So I have 0 0. When S and R 0 0, S bar R bar its complement is 1 1. When S 0 R 1 is 0 1, and when both are 1 1, S and R, their complement S bar R bar becomes 0 0. Okay, and that's what we'll try to see now. Yeah. Now again, either I'll go with this or this. I won't start with the inputs when both are 0 0 or 1 1. Okay, so I'll go with always the complement value. So now S0 R1, that means S bar 1, that is the first combination I'm going with. S bar 1 and R bar 0. And for me, the inputs are these two. Okay. Okay. Why and all we'll see later. Okay. S0 R1, correspondingly S bar is 1 for this NOR gate, NAND gate 1, and for the NAND gate to one of the input, that is R bar, is 0 because R is 1. So now which output of which NAND gate output I can define?
2.
2, that is Qn plus bar is 1, that is this is 1, and this goes as a feedback over here. And S bar is 1, 1 and 1. What is my output? Output will be simply 0. ANDing of 1, 1 is 1. Its complement is 0. And this is 1. Okay. Again, when S is 0, R is 1, what is happening at the output now? Fast. When S is 0, R is 1, Q, out, yeah, it is again reset. Okay. That is the reason why we are giving kind of S bar and R bar and why we are changing the output. Okay, so this is what, irrespective whether we build our NAND using whether we build the SR latch using NAND and NOR, the logic should remain 1. Okay, so this is what, and similarly I can say when S is 1, R is 0, is S bar and R bar becomes 0 1. This is 1 and this is 0. Okay, this is what I mean by the set. And when S and R both 0 0, S bar R bar are 1 1, I can't define. I'll get the feedback, and this is what I'll be getting. This is Qn and this is Qn bar. And when S and R both 1 1, its complement S bar R bar becomes 0 0, and its Qn plus 1 and Qn plus 1 bar becomes 1 1, which is an invalid for me. Okay, this is the invalid. Okay, this is all about your NAND based SR latch. Okay, and now we'll see the corresponding, okay, the NAND based, okay, CMOS SR latch. And for the NAND based, how I should connect my NMOS transistor and how I should connect with respect to PMOS for each of the NAND. I have NAND 1 here and I have NAND 2. So construct each NAND gate using CMOS. So how to connect the NMOSs in for the NAND logic?
Series.
That is basically NAND is nothing but what? Complement of AND. AND goes with this. Okay. So this is one of the transistor. Okay. This is another. So this is, I call it as M1 again. This I call it as M2. They are connected in series, and this is grounded. And similarly, how to go ahead with my PMOS? They should be connected in parallel. Okay. This is my VDD, and these two shorted. And one of the input for this is S, and these two are same now. Okay. And now these two will become common. Yeah. And what I should get basically for this is my Q. Okay. And this Q I'll be getting from the output of the NAND gateway. And what is the output I'm getting over here? Sorry, this is Q. This has to be Q bar now. Okay. And similarly, I can construct a NAND gate 2, okay, with M3. Okay. This is my M4. Correspondingly, I will have the 2 PMOS of that connected in parallel. VDD. Just take out this, just to ensure that it is there. Okay. So this is my R, and these two are connected now. Okay. And this is basically my Q form. Yes. So this is shorted. Okay, this is cool. And typically this I'll go with Q bar. Okay, this is what we're doing. So this is fine. Yeah, output of the NAND gate 1 acting as a one of the input for NAND gate 2, and this is grounded for me. Yes. So this is your NAND based CMOS SR latch. Okay. And similarly, you can find out what is your tau with respect to this SR latch using the NAND. Yeah. Hope this is fine.
So
Okay. So CMOS NAND based CMOS SR latch and the NOR based CMOS SR latch. Okay. So without any enable input. Okay. So now we'll see the clock enabled or clocked. Okay. Or sometimes they call it as a clock enabled. Okay. Either it is clocked SR latch or enabled SR latch kind of. Okay. Or it is called as clock enabled. Okay. latches. I'm still in latch. I'm not going ahead to the master slave. Okay, it's still a latch. So we saw two versions of latches. Just not the enabled or the clock. Okay, this is NOR based latch. Okay, yes, R, Q bar, Q. Now the moment S and R changes, my output changes. Okay, there is no kind of enabling this latch. Okay, this is NOR based. Okay. Now I have to provide one enable input, and that enable may be either I call it as a E on enable input, or it may be a C, or it may be a clock enabled, whatever. Okay. So now how to have a control now? So when enable or C or clocked enable, if this is 1, then latch should be enabled. Then I can define my output with respect to inputs. The moment enable or the clock enable is 0, the latch should be disabled, meaning even though my S and R changes, my output should not change. Okay. So what logic I have to use over here now?
And
It's an AND operations, right? So that means this becomes one of the other input now. So that means there is a 2 stage of gates now. Okay. One for the top. So I have an AND logic for here, and one more AND for the bottom. Okay, and one AND. So similarly, NOR1 and NOR2. Now tell me, what is this input? That is one of the not. So one of the AND gate one input is enable or clock, and one of the AND gate input of second is again enable or clock. So what is the input for the this one now? One of the input, other input of the AND gate one. First,
yes,
it is S, and this is my R. Now you can see when E is 1 or C is 1 or clock enable is 1. So both one of the input of AND gate 1 and one of the input of AND gate 2 are 1. And my output of this depends upon the other input. So this will simply flow. If S is 0, the output of AND gate is 0. If S is 1, output is 0. So that's why it is yes. Similarly, when enable or the clock enable, whatever you call, of one of the input of the AND gate 2 is 1 means this will simply propagate to the output. Yes. Now what happens when enable is 0 now? Yes. What happens when the enable pin is 0 now? What is the output of the AND gate 1 and what is the output of the AND gate 2 first?
0.
0, 0. 0, 0. No, it is not change. I'm just asking the output of the AND gates. So it is 0, 0. The moment, and we know that this is basically NOR based SR latch. Yes. And when the inputs are 0, 0, I'm sure this is my Qn plus 1 bar and this is my Qn plus 1. There is no change, right? Okay. That's what. Whenever I'm disabling means output will be remaining the previous. There is no change. Even though my S and R changes here, there is no change in my output because the flip flop, I mean the latch is disabled now. Okay. When it is enabled, S and R propagates, and depending upon S and R, I'll get the output corresponding. The moment when enable or the clock enable is 0, S and R doesn't propagate. Okay, the NOR gate 1 of the input will be 0, and the NOR gate 2 one of the input will be 0. So the output will be no change, and that's what we have already seen. This is what really happens using this. Now coming to the NAND based. So this is just a recap I'm doing. If you have forgotten, you can. Now this is using NAND. We have already written. Yes. This is Q. This is Q bar. Make sure that your output of NOR gate 1 is complement output. NOR gate 2 is uncomplement. Whereas for NAND gate 1 is its uncomplement. Okay. And this is where we add S bar. This is where we add R bar. Right. And again, we will have either enable or clock enable. Now tell me what logic I have to use now. And
No.
make sure that when S bar is 1, then only I get here output is unchanged. Hope this is fine with everyone. Yes, you can see this previous. You can see this previous. Only when S bar R bar 1 1, meaning S and R are 0 0. Only when S bar R bar 1 1, my output will be previous state. Okay, so that's what. That is important for me now. Now tell me what logic I have to use at the first stage in order to get everything going fine now.
NAND.
It is a NAND. Okay, so one input will be the enable. Yes. Similarly here, this is NAND gate 1 and 2. And now tell me what should be this input now. What should be the one of the input of it is S and here it is R. Now it is interesting, right? When enable is 1, and what is this now? This part, this is still the NAND based SR latch. And the moment if you have the left part, it is the enable kind. That's it. Okay. So now when enable is 1, meaning one of the input of NAND gate 1 is 1, and one of the input of NAND gate 2 is 1. Okay. Now when S is 0, what will be its output of the NAND gates 1? When is 1, and when S is 1, output will be 0. Okay, and that is the beauty of this NAND gate, right? If one of the input is fixed to plus VCC, okay, what is the output I'm getting? If this is A, it is the complement. That's why this is S means this is S bar, this is R means this is R bar. Okay, now you understood why we are taking this S bar and R bar. So these two are still latches, but they are enabled or controlled latches. I have a control on these two latches, okay, either by enabling or disabling. Hope this is fine. Yes.
Yes, sir.
Yeah, you can construct the SR latch, okay, for this enabled or clock, and make sure that when I say what is the difference between a flip-flop and latch, don't say that flip-flop requires a clock and the latch requires a clock, does not require a clock. No. The clock are basically a enabled inputs for me. They're all synchronous. Hope this is fine. Yeah.
Yes.
Latch also requires an enable. This clock is basically an enable input. Since we are giving a continuous cycles of inputs, the signal, that's why it is called as a clock. Okay. But what is latch now? What is a latch?
It's trigger.
It's triggered. Level sensitive.
Flip.
It's a level sensitive. Okay. Meaning when both either the NOR based or NAND based are enabled, okay, outputs will change based on the inputs S and R. Okay, output will change corresponding to change in the input. It doesn't depend upon the rising edge or the falling edge of this enable or the clock. That is what I mean by. Is that clear? Level sensitive means irrespective of my enable. Okay, if enable is 1, okay, meaning I'll just draw over top here. Okay, if this is my enable input or a clock, whatever you call enable or clock enable. Okay, this is 1, this is 0, this is 0. Okay, when 0 means the flip flops are disabled. When this are 1, it is enabled. Okay, this is the fine example I can. Okay, then now S is 0, R is 1. Initially, I assume Q to be 0, Q to be 1, and Q to be 1. That's it. Okay. And this is what is happening now. Okay, and I'll just go with one half cycle and then so now at t is equal to t naught. Okay, so this is my time cycle t naught. S is becoming 1, R is becoming 0. What should happen to my Q?
1.
1. Okay, as since it was 1, it will remain 1. But you can see that still my flip-flop is enabled here. My S is becoming 0 after some time, and this I call it as something like T naught, T1. S is 0, R is 1. So what should happen to my output?
0.
0. It should go down, and it will be same until it is changed. And again, S is becoming 1, R is becoming 1 when my flip-flop is still enabled. Okay, and what should happen? Again, it should change. It will change to 1. And then since the next half cycle is disabled completely here, okay, irrespective of S and R, my output remains in the previous state. Previous is 1 means it will remain 1. Okay, and you can see that this is very important for me. Yes, when my flip-flop is enabled, that is latch is enabled, okay, output change with respect to input. That means now this particular latch is nothing but what? It is level sensitive with respect to this enable or the clock. Is that clear now? Yes. My output keep changing with respect to S and R with respect to the level of my enable or clock. Enable or clock. Okay, that's what we mean by yes. Whereas master slave and edge triggered, what really happens is this is what I'll just show in the next. Again, I'm saying it's a recap. Again, I'm saying it's a recap. Okay, this is my enable or clock enabled. This is 0 1 0 1 and S and R. And I'll just take the same kind of waveform over here. Okay, 1 0 1 0 and 1. Initially, this is at 1. This is at 0. Goes to 0 here. 1 here, 1 and then 0. Okay, this is my T naught. This is my T1. This is my T2, and this is my T3. Okay. If it is a master slave and edge trigger, both are kind of same. Okay. Now, if it is a positive edge trigger, meaning this is what, right? All of you agree? Yes. Now, only at the rising edge of the this is enabled. Only at this instant. This is disabled. Rest all is disabled, right? This is disabled. This is disabled. Only at the rising edge of my enable or the clock input, the flip-flop is enabled. Okay. So at this edge, my S is 1, R is 0, assuming that previously Q is 0 means, okay, at time T naught, what should happen to my Q now? Yes,
1.
it should become 1. It goes 1. It goes 1. And then immediately after that, what is happening to my flip-flop? What is happening to my flip-flop? Fast. My flip-flop is enabled only at the edges of my enable or the clock input. And anything previous to this or anything after to this, it will be disabled. So that's why, since the flip-flop is disabled, output remains 1 for the entire half duration of this. Is that clear now? Yes?
Yes, sir.
And this output is now is called edge triggered. That means output doesn't vary to S and R, even though S and R are changing. When clock is or enable is completely 1, output is not changing because this flip-flop output is enabled only during the edge trigger. Whereas in the previous case, if you see, okay, here the flip-flop output, okay, okay, this output, okay, is with respect to your level sensitive. Is that okay? Okay, that means until unless my E is 1, output is sensitive to S and R. Whereas here, output is sensitive only for the edges. And at edge, if S and R, based on S and R, my output is changing. Rest all, it will remain this. Okay, so that is what your difference between an edge triggered and a level sensitive. So your latches basically are level sensitive. Your master slave is a pulse sensitive, but pulse is very small. it is equivalent to my edge trigger. That's what we say. Okay, and these are the two things now. Okay, so build the circuit for clock enabled or controlled NAND based SR latch as well as the NOR based SR latch. Oh, this is fine. Yes.
Yes, sir.
Yeah. So these are the two things that we have now, and that's what. Next, we'll try to see. I mean, this is the way, even the corresponding waveform also you have to write when we ask. Okay, because it is already known. So in the next class, we will take up of the master slave sender. Okay, and also the CMOS logic. Okay, or the CMOS structure of the master slave with respect to, again, when I say master slave, we have SR latch master slave, you have master slave JK flip flop, you have master slave D flip flop. Okay, all are constructed. Yeah? So I will stop here and we'll continue in the tomorrow's class, that is 11:50. Yeah, any clarification doubts?